Good morning, students. Today we will discuss subspace of a Banach space, seminorm and its properties, and the product of normed linear spaces. So our first topic is subspace of a Banach space. So there is a theorem based on this which states that a subspace Y of a Banach space X is complete if and only if Y is closed in X. Means if we have a Banach space, then if the subspace is complete, then it is closed, and if it is closed, then it is complete. So let us take firstly that Y is complete subspace in X, and we prove that Y is closed. Now, in order to prove that Y is closed, we will have to prove that Y is equal to Y closure. Now, because every set is contained in its closure, so Y is contained in Y closure. It means we have to prove that Y closure is contained in Y. So let us take an arbitrary point belonging to Y closure. So let us take X belongs to Y closure. It means X is closure point of Y. Now, by definition of closure point, if X is closure point of Y, by definition there exists a sequence Xn in Y which converges to X. Now, we prove that this Xn is quasi-sequence in Y. Now, because the sequence Xn is convergent and it converges to X. So by definition of convergence, for given epsilon greater than 0, there exists a positive integer. We have taken that positive integer capital N, such that for all n greater than or equal to existing integer, the norm of xn minus x is less than epsilon by 2. So here we have applied the definition of convergence of a sequence in a normed linear space. Now, to prove the sequence is Cauchy, let us take n and m greater than or equal to n. Now, let us consider the norm of xm minus xn. Now, by adding and subtracting x and using the triangle inequality of norm, by using triangle inequality, this will be less than or equal to xm minus x norm plus xn minus x norm. Now, as we already discussed, because the sequence xn is convergent, so this will be less than epsilon by 2, and also this quantity is also less than epsilon by 2. So we have obtained xm minus xn norm that is less than epsilon. So by definition, we can say that the sequence xn, that is a Cauchy sequence in Y, but we are given Y is complete subspace of X. So by definition of complete, we can say that every Cauchy sequence is convergent in that space, and also the limit of convergent sequence in a metric space is unique. So we can say that xn converges to X, and here X belongs to Y. So we have proved that X belongs to Y closure implies that X belongs to Y. So we have proved Y closure is contained in Y, and also Y is contained in Y closure. So combining the two expressions, we get Y is equal to Y closure. It means Y is closed. Now we will prove the converse part. Conversely, we are given that Y is closed, and we are to prove that Y is complete. In order to prove Y is complete, we will have to prove that every Cauchy sequence in Y is convergent in Y. So let us take an arbitrary Cauchy sequence in Y. That Cauchy sequence, we have taken the sequence xn. So let xn be Cauchy sequence in Y, but because Y is a subspace of X, so this will be Cauchy sequence in X. Now X is complete space because that is Banach space, and Banach space means complete norm space. So X is complete. So by definition, every Cauchy sequence in X will be convergent in X. So this Cauchy sequence Xn will converge to X, and this X belongs to X. But then X belongs to Y closure by using this result, because we know that an element X belongs to M closure if and only if there exists a sequence Xn in M which converges to X. So X belongs to Y closure, but Y is closed. If Y is closed, then Y closure will be same as Y. So from here X belongs to Y. So we have proved that the sequence Xn converges to X and X belongs to Y. It means every Cauchy sequence in Y is convergent in Y. So by definition, Y is complete. So this completes the theorem that a subspace Y of a Banach space X is complete if and only if Y is closed in X. Next topic is semi-norm. We already discussed norm. If from the norm we exclude the second property of norm was norm is 0 if and only if the element itself is 0. If we exclude that property from the definition of norm, then it becomes semi-norm. So let us define what is semi-norm. A semi-norm P on a vector space X is a function which we have denoted by P, and this function P is defined on the vector space X to the space of real numbers, and it satisfies the three properties. First property, it is non-negative, means P of X is greater than or equal to 0 for every vector X belonging to the vector space X. Second property, absolute homogeneous property, means P of alpha X is equal to alpha mod into P of X, and this is true for every X belonging to the vector space X. Third property, triangle inequality, P of X plus Y is less than or equal to Px plus Py, which is true for every vector X and Y belonging to the vector space X. Now let us have some examples to show that every norm is a semi-norm. This is true by definition, but converse is not true. We will show this by an example. So let us take an example. Show that Px defined by the mod of limit xn as n approaches to infinity. We show that this P defines semi-norm on the linear space C. Linear space C is the space of all convergent sequences. Here, this kind of sequences, if we take X belongs to the sequence space that is of this form, Xn, sequence Xn, we will show that this P is a semi-norm on C, but not a norm on C. So let us firstly show this is a norm on C. So first property, that should be non-negative. Now, by definition of P is defined by the absolute value of the limit of Xn as n approaches to infinity, because modulus is always non-negative quantity. So we can say that Px is greater than or equal to 0. Now, second condition, absolute homogeneous property. So let us take an element X belongs to this linear space C. Now by definition, X belongs to C means X is a convergent sequence. We have denoted that sequence by the sequence Xn. Now alpha into X means the sequence formed by multiplying alpha with the elements of sequence Xn. Now let us find P of alpha X. By definition, P of alpha X means mod of limit of alpha Xn. Now this can further be written as alpha mod into mod of limit Xn. Now by definition, mod of limit Xn, that is P of X. So we get P of alpha X is equal to alpha mod into P of X. So this proves absolute homogeneous property. Now third property, triangle inequality. So let us take two elements X and Y belonging to the linear space C. By definition, X is given by a convergent sequence, we have taken Xn, and Y is also a convergent sequence, we have taken Yn. Now let us find P of X plus Y. Now by definition of P, this is the mod of the limit of Xn plus Yn. Now limit of Xn plus Yn, that can be written as limit of Xn plus limit of Yn. Now by using the triangle inequality of modulus, this is less than or equal to mod of limit Xn plus mod of limit Yn. Now by definition, this is P of X, this is P of Y. So we have proved that P is a semi-norm on the linear space C. Now we will show that this P doesn't define a norm. Now to show that P doesn't define a norm, we prove that Px is equal to 0 does not apply X is equal to 0. Does not imply X is equal to 0. So let us take an example. Let us take X defined by the sequence Xn, where sequence Xn is having the elements 1, 1 by 2, 1 by 3, 1 by 4 and so on. Means Xn we have taken 1 by n. Now clearly this X is not equal to 0. But if we find P of X means mod of limit of Xn. Now because Xn is 1 by n, so as n approaches to infinity, 1 by n approaches to 0. So P of X will become 0. So we have shown P of X is 0, but X is not equal to 0. Thus Px is equal to 0 does not imply X is equal to 0. So this proves that P is not a norm on C. Now next is a property of semi-norm. Show that the semi-norm P on a vector space X satisfies the following properties. First property, P of 0 vector is 0, and second property, P of X minus P of Y mod is less than or equal to P of X minus Y for every X and Y belonging to the vector space X. Now to prove this, let us first prove the first property. Now P of 0 vector. Now 0 vector can be written as 0 into X. So now by using the absolute homogeneous property, which states P of alpha X is equal to alpha mod into P of X. Here alpha is some scalar. So by using this property here, this will become mod of 0 into P of X. Now mod of 0 is 0, so 0 into Px, that will be 0. So we have proved the first property. Now in the second property, let us consider vector X belonging to the vector space X, and let us find P of X. Now we can add and subtract Y inside, and by using the triangle inequality in the semi-norm, this will be less than or equal to P of X minus Y plus P of Y. Now shifting this term to the left side, we get P of X minus Py is less than or equal to P of X minus Y. In the same way, we can find P of Y by adding and subtracting X and using the triangle inequality of semi-norm and shifting the term Px to left side. We get P of Y minus P of X is less than or equal to P of Y minus X. Now P of Y minus X can also be written as P of X minus Y. Now combining these two, we can say that Px minus Py mod is less than or equal to P of X minus Y. So this proves the property of semi-norm, which is defined on the vector space X. Now our last theorem is the product of two norm spaces. Let us take two norm spaces. First norm space we have taken X1 and the norm corresponding to this space, that is denoted by the suffix 1 in the base. And X2 is also a norm space with the norm denoted by the suffix 2 in the base. These are two norm spaces, and let us take their product vector space, which is denoted by the Cartesian product of the norm space X1 and X2. Then we prove that this product vector space becomes a norm space if we define X norm is equal to the maximum of the norm of vector X1, where X1 is a vector belonging to the norm space X1 and X2 is a vector belonging to the normed space x2. So the function defined by x norm is equal to maximum of x1 norm and x2 norm. We proved that this defines a norm on the product vector space x. Here the suffix 1 will denote the norm on x1 and suffix 2 will denote the norm on x2. And here this ordered pair belongs to the product vector space x. So let us verify the properties of norm. First property, we have to check norm of x is non-negative. Now because norm of x is defined by the maximum of the norm of vector x1 and norm of vector x2. Now because norm of vector x1, this is defined on the norm space x1 and x1 is a norm space and therefore this norm will be non-negative for every vector belonging to x1. In the same way, x2 is also a normed space. So the norm of vector x2 is non-negative for every x2 belonging to the normed space x2. Because both are non-negative, so their maximum value, that will also be non-negative. So this proves first property of norm. Now the second property, let us take a vector x belonging to the product vector space. And this is denoted by the ordered pair formed by the vectors x1 and x2. Here this x1 belongs to the normed space x1 and x2 belongs to the normed space x2. Now let us take norm is 0. Now by definition of norm is 0 if and only if the maximum of norm of x1 and x2 is 0. So from here, if and only if norm of x1 is 0 and norm of x2 is 0. Now because x1 and x2 are normed spaces, so if the norm is 0, element itself is 0. So if and only if x1 is 0 and x2 is 0. Now because x1 and x2 both are 0, so ordered pair formed by them will also be 0. So we have proved norm of vector x is 0 if and only if x itself is 0. Now next property, absolute homogeneous property. Let us take alpha be a scalar and a vector x belonging to the product vector space denoted by the pair x1 x2. Now let us find norm of alpha x. Substituting the value of x here and multiplying this vector by alpha, this will become norm of alpha x1 alpha x2. Now by using the definition of this function, this is maximum of alpha x1 norm, alpha x2 norm. Because x1 and x2 are normed spaces, so this will become mod of alpha into x1 norm and this is mod of alpha into x2 norm. And this can further be written as alpha mod into maximum of x1 norm comma x2 norm. This is x norm, so this proves absolute homogeneous property of norm. Now the last property, triangle inequality. Let us take two vectors x and y belonging to the product vector space. By definition of product vector space, x and y will be ordered pairs. So x is the ordered pair x1 x2 and y is the ordered pair y1 y2. Now let us find x plus y norm. Now x plus y means the sum of these two vectors. So this will become norm of x1 plus y1 comma x2 plus y2. Now by definition of this function, this is the maximum of x1 plus y1 norm comma x2 plus y2 norm. This norm is defined on the norm space x1. This norm is defined on the norm space x2. Now because x1 and x2 are normed spaces, so triangle inequality will be satisfied in both. So this will be less than or equal to x1 norm plus y1 norm. And this will be less than or equal to x2 norm plus y2 norm. So substituting the values, we get x plus y norm is less than or equal to maximum of x1 norm plus y1 norm comma x2 norm plus y2 norm. Now we can write this in the form, this is less than or equal to maximum of x1 norm comma x2 norm plus maximum of y1 norm comma y2 norm. By definition, this is x norm and this is y norm. So we have proved x plus y norm is less than or equal to x norm plus y norm. So the function defined by this defines a norm on the product vector space x. So we have proved that the product of two normed spaces also becomes a normed space when we define the norm in this way. And this completes this topic.